So now we're going to begin Unit 2, which focuses on linear relations and functions, as well as their graphs. And this is, again, pretty much a review of Algebra 1 with a few tidbits added in that may be extensions of things or embellishments of things or different ways of looking at things that you've already been exposed to. So in this first set of notes, we are going to explore the rectangular coordinate system. It's also called the XY coordinate system. It's also known as the Cartesian coordinate system, or really even the Cartesian plane. And this is named after a French mathematician named René Descartes. So you've seen this before. This is just the XY plane. So this horizontal axis is known as the x-axis. The vertical axis is known as the y-axis. We are known to write equations where we have an input and an output. So our input values, also known as our independent values, are x values. And we're going to do some rule to those x values, and we're going to get what is known as our output values. So they are dependent on what we do to the x values. So x is independent, input, y is dependent, output. So those are the two axes that you should be familiar with. And then in addition to that, we see that these two axes are perpendicular. The x and the y-axis meet at 90-degree angles, and they kind of cut up this plane that in fact goes on forever and ever, but we're only seeing a little piece of it, into 4 quadrants. So here is our first quadrant, known as quadrant 1. Then if we move in a counterclockwise directions, we have quadrant 2. And then we keep going in a counterclockwise manner, and we have quadrant 3. And then we keep going, and to the right, we have quadrant 4. So there are very specific properties that we have associated with the x and the y values for each of these quadrants. So while we have what is known as the origin, where the x and the y-axis intersect, that is known as the point 0, 0, the ordered pair 0, 0. We write the x value first, the y value second, kind of like alphabetically. Now, if we look at the values of each of the ordered pairs in each of the quadrants, you should be able to recognize that in the first quadrant, we're going in the positive x direction, positive y direction, so those ordered pairs are going to have both the x and the y value positive. Now, if I move to quadrant 2, I notice that I'm going in the negative direction for x, but still the positive direction for y. So all ordered pairs that fall in the second quadrant are going to be minus plus, negative positive. Continuing in the third quadrant, I'm going to the left in the negative x direction and down in the negative y direction. So all ordered pairs are going to have a negative x and a negative y value. And last but not least, in quadrant 4, what are we going to have? X's are going to be in the positive direction, but y's are going to be in the negative direction. So I could plot points given an x and a y value, and depending on those signs, I know where to place them on the Cartesian plane. Now, the term relation. What is a relation? A relation is a pairing of input and output values. In other words, X and Y values, most often known as ordered pairs. And again, they are represented as an ordered pair, the X value first, then the Y value. And what we refer to as the domain of this relation, this pairing, is the set of input values for which the relation is defined. Those are our X values. Range values of the relation are the output values or the results after performing some rule, substituting the domain into some rule, and they are known as your Y values. So your ordered pairs are X and Y, the X values are your domain, the Y are your range. So let's say I give you a table of values. Notice that you have X values. These are your input values, also known as your domain values. And you've been given some Y's in the second row, which are your output values, your range values. Now, I've given you some ordered pairs, and what if I say, there's got to be a rule, something that I'm doing to the X values to get the Y values. So again, I have written this in terms of what's known as a T-table, or a table of values. Oops. So we have a table of values, T-table, and I want to try to figure out the rule. So we're thinking, what am I doing to X to get Y? So try to figure out the rule. Y'all think about that. What am I doing to my inputs to get my outputs? Now, there's many different ways I can represent this data. I could actually state the rule. I could state the rule in terms of words. Hopefully you came up with this. What am I doing? Oops, I'm writing really fat marker. I'm going to add 7 to my input to get the output. If I were writing this in words, that's what I would say. Now, what am I doing? I am adding 7 to my input values to get my Y values, right? So when X is 1, I add 7 to it, I get 8. X is 4, I add 7 to it, I get 11. X is 7, I'm going to add 7 to it, I get 14. So what would the corresponding output value be for my input of 3? Well, I'm going to add 7 to it, and I'm going to get 10. Now, so we've stated the rule in words. We could actually write an equation. But what if I wanted to represent this information, this table of values, this set of domain values and range values, this set of input and output values? What if I wanted to write that as a mapping? So instead of a table, instead of a rule, I want to write it as a mapping. Well, the way you write it as a mapping is you literally create little ovals or some shape. And I'm going to say every number I put in here is going to be an input value. So let's see, I have 1, I have 3, I have 4, I have 7. And then I'm going to draw another oval that represents my output, my range values. And here I have 8 and 10 and 11 and 14. And I'm honestly going to just draw arrows from the input to the corresponding output. So this would be a mapping. This shows my input and my output. Now I could also take this same information and represent it as ordered pairs. So all of these are different ways of representing the same information. Ordered pairs. So I'm literally looking at, I don't have any other colors. Oh, goodness gracious. Well, let's try this. No, that's yellow. Gray. That's an ordered pair. That's an ordered pair. That's an ordered pair. That's an ordered pair. And how do I write ordered pairs? As the X and the Y value. So I'm just going to list my ordered pairs. And then I could take the same information and I can say, okay, well, what is the domain? What is the domain? Oops. My domain is just my set of input values. So I would list my domain, 1, 3, 4, 7. And I could even call it a set, my set of input values. And I could do the same thing for my range, and I could maybe call that set R. And I could write all of the output values. So that would be my range. So all of this is, given a set of values, you should be able to figure out the rule, draw a mapping, represent these points as ordered pairs. You should be able to identify the domain and the range. And last but not least, you should be able to graph this information. So if I wanted to graph this information, this is what's known as a discrete graph. And the reason it is a discrete graph is because I'm just graphing those points. I know nothing else but those points. So if I look at my X values versus my Y values, and it doesn't matter how you're counting, I could go ahead and count by ones and just label these. And I would plot my points. Now I'm in the first quadrant because my X values and my Y values are both positive. So when X is 1, Y is 8. So let's see if I can count that. 1, 2, 3, 4, 5, 6, 7, 8. And then when X is 3, Y is 10. And when X is 4, Y is 11. And so on. And so I just have discrete, distinct points. I'm not connecting them. Unless you are specifically given the linear equation, the rule. I'm not saying it's true for all x's. It's not continuous. It's discrete. So let's think back. A relation was a pairing of an input and an output value. Well, some relations are very special. Special relations are functions. You must know the definition. This is the definition of a function. You need to know the definition of a function. Hint, hint, hint. You better be able to state the definition of a function. A function is a relation where there is only one output for each input. Every element in the domain, every input value is mapped to exactly one output value, one range value. And if I were to graph a linear function, the graph of a linear function is a line. So, based on what we just did on the previous page with relations, can we state 6 different ways to represent a function? All functions are relations. Not all relations are functions. That's important. So what are 6 different ways I can represent a function? Can you name the 6 different ways? Think about it. See if you can remember or look back and see. A rule, whether it's in words or an equation. Well, this actually, a rule would be an equation. So let's go ahead and separate that. Words, a description. We had a t-table, just a table of values. What other ways can we represent a function, or a relation for that matter? A mapping, a graph, or using ordered pairs. You should be able to know different ways to represent them, and you should be able to go from one to the other. If I give a mapping, can you write the t-table? If I were to give you the words, can you write the rule? If I were to give you a t-table, can you give me the ordered pairs? You should be able to. Now, in the next section, you have been asked to state the domain and the range of the following relation. So you've been given a pairing, set of inputs, outputs, ordered pairs. Can we identify the domain values? Well, yes. They're just the x values. So if I were to write that set representing the domain values, remember, for a set, we use set notation. We write the numbers in ascending order, and we don't repeat any numbers. So what is the domain? Go ahead, take a look. Can you figure it out? -7, -2, -1, 0. Okay, let's do the same thing for the range. Can we identify the range values? There are y values. So the range as a set in ascending order, not repeating any numbers, -7, -2, -1, 0, and 4. So my question to you is this relation a function? Using the definition, no, it is not. Why not? Well, notice some of your inputs, for example, -7 has different outputs. -2 has different outputs. Every input has to have only one output for it to be a function. So, here you've been given some tables. What you're to do for each of these is you are to look at your table of values, and you are to state the domain, state the range, and then determine whether or not it's a function, and why not. So, domain. If I'm looking at my domain values, I'm looking at my input values. What are they? -3, -2, -1, 0, 1. Range values. Those are my output values. What is my range? -6, -1, 0, 3, and 15. Is this a function? Well, do every single input value go to a different output value? Yes, it's a function. Try the others. See if you get them right. Try it on your own. If you were in class, you'd be doing this. I wouldn't give you the answers just yet. Try them. Pause the video. Input, input, domain, domain, range, range, range. Domain, range. Okay, so you should be able to look at the tables and immediately identify the domain and range. I do want to point out the fact that if you have repeating numbers, for example, here in my output, my range value is just 6. I only write it once. Don't repeat the numbers. Same thing here. We're not repeating these numbers. There's no need to put the -1 twice. That's not proper set notation. Now, let's think about it. Is the second example a function? Yes or no? By definition. You may be looking at those -6s and they're repeating, but those are repeating outputs. Every input has its own output, even though those outputs are repeated. They're for different input values. So is this a function? Yes, it is. Is the next one a function? Yes or no? -1 goes to a whole lot of different outputs. So no, it is not a function. No. Is the next one a function? Now you may be looking at this one and say, oh, but the -2 is repeating. Yeah, but it goes to the same output value. So yes, this is a function. Don't get fooled. Now here's a word problem. Evelyn makes $5 per hour at her new job. If T equals time, time worked, T equals time worked in hours, and D is dollars earned, can we pick some values of P and compute the corresponding values of D? Now, are there any restrictions on the T values I can choose? Let's think about this real-world example. T represents time. So can time be anything? No. Time has to be positive. I can only choose positive values for time. Does it matter? No. I can have 0. I can choose whole numbers. That makes sense. And then I could think to myself, all right, she earns $5 for every hour, so can you write the corresponding output values? If so, how are you getting them? Well, if she works no hours, she doesn't make any money. If she works 1 hour, she makes $5. If she works 2 hours, she makes $10, and so on. So my question to you is, well, is it a function? Well, if I look at those input values, they go to only one output value. So yes, it is a function. The amount of money she makes, D, the output, depends, is a function of the time she works. So can we write the equation? Can we write the equation for using T and D? Well, D, the amount of money she makes equals what? $5 for every hour of time she works. So that would be the corresponding equation. Now, we have rules. We have linear equations, mappings, pairings of inputs and output values. So if I were to give you this equation, that represents a function. What is the rule? Y equals multiplying the input x times 3 and adding 7. That's the rule. Can we graph that line? Do we know a trick to graph the line? Well, let's say you don't know how to graph a line. Well, what can you do? You could create a table of values. Are there any restrictions on the x values, the domain values that I choose? No. So I can choose any ones I want. So I'm going to choose some negative, 0, and some positive numbers. And I'm literally substituting in those values for x. So if I say, what is the y when x is -3? Well, 3 times -3 is -9. -9 plus 7, -2. Do the same thing for the rest of the x values. See if we get the same table of values. Substitute in these x's and see what the corresponding y's are. There you go. Now, here's our table of values. I can convert those to ordered pairs, which are the solutions to this equation. Because if I were to substitute those x and those y values back into the original linear equation, I would get an identity. So they are, in fact, solutions. So what are the corresponding ordered pairs? Remember, we write the x value first and then the y value. So there are my corresponding ordered pairs. And then what could I do? I could then take those ordered pairs and I could plot those points. Make sure you always label your axes. These are labeled, but I want you to get in the habit. So -3, I'm plotting points, -3, -2, I'm plotting a point, -1, 4, 0, 7, 1, 10, 3, 16. So I have plotted each of these points. Since this is a line, it's a linear equation, I'm going to do the best of my ability to graph this thing. Let's see if I can get a ruler on here. Ugh, it's kind of ugly. I tried. There we go. You should have a ruler. Make your things pretty. I'm trying to do this on an iPad. It's not so pretty. But there's my line, and it should pass through all of those points. There we go. I could fudge it a little bit. There we go. So this is the graph of the line y equals 3x plus 7. Now, this line we see passes through the x-axis and passes through the y-axis. The point where the line passes through the y-axis is known as the y-intercept. This point is always represented with the x value being 0 and the y value being, well, the y value of the point that passes through the x-axis. So how could I find that? To find the y-intercept, I could easily set x equal to 0 and solve for y. Similarly, the point where the line intersects the x-axis is the x-intercept. It is the x value of the point that passes through the x-axis, and the corresponding y value is 0. So to find the x-intercept, I literally set y equal to 0 in the equation, and I solve for x. So that's a quick and easy way to get those intercepts. And in fact, instead of making a table of values and getting a set of ordered pairs and plotting those points and connecting those points, you can, to graph a line, especially if depending on the form in which you've been given it, just find the x and the y intercepts by using this information. Plot those 2 points because you only need 2 points to graph a line. So if I want to find the x-intercept, what did we say we needed to do? Well, we're going to start with this equation, and we are going to set y equal to 0. So I'm going to set y equal to 0, and so this term goes to 0, and I'm going to solve for x. And hopefully you know how to do this. This is telling me that x equals 4. So x-intercept is the point where the line, the graph of the line, crosses the x-axis. So we have x equal 4, y equals 0. Now, I know some things, they don't make you write it as points, maybe my math lab, maybe standardized tests, but really it's a point. You should write it as a point. Now let's look at the y-intercept. Y-intercept. Where does the graph of the line cross the y-axis? Well, what do? We start again with the original equation that has been given. And now what do? We set x equal to 0. So now I'm going to let x equal 0. So that means this term goes to 0. I'm going to solve for y. So y equals -8. Again, an intercept you want to write as a point. The y-intercept always has the x value as 0, and then we found y. Now, with these 2 points, I can plot those points. So for my x-intercept, it is at 4, 0. That's the point 4, 0. My y-intercept is 0, -8. So I have plotted 2 points all I have to do is connect these 2 points to the best of my ability. There we go. And I get the line 4x minus 2y equals 16. I've graphed it by just plotting the intercepts. Now, slope. Let's talk about slope. So when we talk about lines, we refer to slope. Slope doesn't refer to anything but linear functions. Do not use the term slope to describe other things. Slope is also known as the constant rate of change for a linear function. It represents a constant first finite difference. Only linear functions have a constant rate of change, have a slope. Now there's many different ways to represent slope. This rate of change, known as slope, is often represented by the letter M. Now, where does the letter M come from? Why M? Well, in French, the word for mountain, mont, starts with the letter M. Mountains have steepness. There you go. That's why M. I think so. Now, what does it represent? It represents the rise over the run. How much are you rising? How much are you changing and why? How much are you changing vertically? Change. Change is difference. So if I have 2 y values and I look at the difference, I see the change in the y values, the change in my range values. In all honesty, you really should get in the habit of seeing changes represented as a triangle. In higher level math, that represents change. Just wait till you get to pre-cal and calculus and beyond. So that's your change in your y. Now, that is over your run, your change in domain values, your horizontal change, your change in x's, your difference in x's. That is your slope. So if you are given 2 points, and these little subscripts, so this is point 1, so that's why it has a subscript 1. It has an x value and a y value in the ordered pair. The little subscripts are just saying, hey, that's the x and the y value for the first point. Your second point, I'm going to call P sub 2. It has an x and a y value, but to know which x and y values I'm working with, I have little subscripts 2. So that's where these 2's and 1's come from, if you're wondering. So if I give you a table of values, it's a relation. First thing you should do, is it a function? If it's a linear function, you should be able to identify the rate of change. You should also be able to identify, if given especially, the Y-intercept. So these are functions. For every input, there's only one output. So if I were to look at these, so each of these are ordered pairs, right? That's an ordered pair, that's an ordered pair, that's an ordered pair, that's an ordered pair. But I want to look at my change. So let's look at first our change in x. My change in x. So I'm going to start with the furthest one, y2 minus y1. 4 minus 2, 2. 2 minus 0, 2. 0 minus a negative 2, 2. Oh, I'm getting excited. My change of x is constant, but I'm not done. I now need to also calculate my change in y, because both have to be constant. So negative 1 minus 0, negative 1. 0 minus 1, negative 1. 1 minus 2, negative 1. So my change in y is constant as well. So if I wanted to represent my slope is my change of y over my change of x. Change of y was negative 1. Change of x was 2. So the slope is negative 1/2. It is linear. And that is looking at a constant first finite difference. Constant first finite difference is negative 1/2. Now, can I also look at that table of values and determine the y-intercept? Well, what do I know about the y-intercept? It is the point where the line crosses the y-axis. How do I identify that in the table? I look to see where x is 0. When I'm looking at x equals 0, I'm on my y-axis. So my y-intercept is the point 0, 1. Now, let's look at the next one. Is it a function? Yes, it's a function. Is it linear? Well, let's look at our changes. Change of y. 16 minus 8, 8. 8 minus 4, 4. 4 minus 2, 2. Let's see. Depends on how our x's are changing. Let's look at our change of x. 5 minus 4, 1. Oh, no. Change of y over change of x is not constant. So there is no rate of change. Can I identify the y? Well, we're not even going to do that because it's not a linear function. It's non-linear. Now, are we going to talk about those? Yes, but not just yet. So, let's go back to this information here, and let's use the fact that we have been given 2 points. I'm going to call this point 1 and point 2. It doesn't matter which one I'm calling point 1 and point 2, but I have to denote it. So that means this is the x value for point 1. This is the y value for point 1. This is the x value for point 2. This is the y value for point 2. So if I wanted to find the slope of the line that passes through those 2 points, all I'm going to have to do is calculate my change of y over my change of x. So that means y2 minus y1 over x2 minus x1. So what was y2? y2, negative 5. Minus y1 is 1. x2 is 2. Minus x1, be careful of your minus signs. Let's simplify. And then, well, that's fine. I think I want to go one step further. There's my slope. Let's simplify. Now, can I graph the line if I'm given just a point and a slope? Of course I can. If I want to graph a line that has the slope of 5/2 and it passes through this point, well, the first thing I would do is plot the point. Let's plot the point. If I want to plot the point, and here I'm labeling my axes, -1, -3. There's the point. Now, from that point, I can apply the slope. So my rise is 5. 1, 2, 3, 4, 5. My run is +2. So there's my second point. And then again, all I need are 2 points to graph the line. That's hideous, but you get it. All right. That really is hideous. So that's kind of ugly. Let's make it a little bit prettier. There we go. That's hideous. All right. Now, what if I give you a slope of -3/4, and I say, hey, it passes through this point? Well, look at that point. That's a very special point. Do we know what kind of point that is with the x value 0? Yeah, the y-intercept. You've been given the y. How lucky are you? You've been given the y-intercept. 0, 4. Label your axes. Now, from that point that you've been given, you can apply the slope. Now, the slope is -3/4. I can either go down 3 and to the right 4, or I can save the negative for the denominator. I can't use it twice. I can use it only once. The fraction is negative. So from here, I can go down 3 and to the right 4, or I could go up 3 and to the left 4. Either way, I'm on the line. There we go. There's my line. I'm curious, do you know how to write the equation of that line? Well, if you know what is known as the slope-intercept form of a line, I can write it as y equals mx plus b. Now, what does all that mean? The m is just the slope. The b is the y value of the y-intercept. Do I have that information for the previous problem? I do. Y, if I wanted to write the equation of this line, y equals, what was the slope? Negative 3/4 x. What is the y value of the y-intercept? 4. So there's the equation. Not hard. Now, here you've been given the equation of a line. It's not in slope-intercept form. It's not in slope-intercept form at all. But I want to write the equation that is given in this form in slope-intercept form. So how am I going to do that? I'm going to solve for y. Just solve for the y. I need to have it in this form. So what do I need to do? I need to solve for y. So I need to isolate the y. I need to move everything connected on the left-hand side away from it. So to do that, opposite of minus 4x is plus 4x. Okay, so that makes this go away. So I am, in fact, now left with y equals, and I'm going to put it in the order of slope-intercept form, and there it is. So you should easily be able to identify the slope from here. The slope is 4, or 4/1, if you want to look at rise and run. What is the y-intercept? I look to that b value, and the y-intercept is 0, -1. Now, I could plot that point, 0, -1. I could rise 4, 1, 2, 3, 4, run 1. There's the graph of that line. Beautiful. Let's try another. You try it. Try to put this in slope-intercept form, solving for y. Identify the slope, identify the y-intercept, graph the line. You do it, I do it, pause it, see if we get the same thing. Okay, if I want to isolate the y, what might be the first thing that I would want to do? Well, personally, move that x to the other side so that it's gone, leaving me 3/4 y equals -x plus 6. Now, what's standing in the way of the y being by itself? The 3/4. How is the 3/4 connected to the y? By multiplication. So how do I divide by a fraction? I multiply by the reciprocal. So I'm going to multiply. I'm going to multiply both sides by the reciprocal, 4/3. If I do that, I have to do it to every single term. That means to this one, to this one. So that's going to give me y equals -4/3 x plus 6 times 4/3. And I can simplify that. And so what would the equation in simplified form be? Y equals -4/3 x plus 8. There it is in slope-intercept form. What is the slope? -4/3. What is the intercept? Y-intercept? 0, 8. I can plot that. 1, 2, 3, 4. 1, 2, 3. Label my axes. Graph the line. Now, there are very special types of lines. Horizontal, vertical lines. Horizontal and vertical lines have very special properties. So let's talk about what the equation of a vertical line looks like. The equation of a vertical line is always going to be x equaling a number. So for example, x equal, I don't know, let's say -3. So vertical line at x equal -3. Well, when x is -3, I'm here. Every point on this vertical line has an x value of -3. So like -3, 0, -3, 4. I don't care where you are. You're always an x value of -3. For a horizontal line, written in standard form, it's always y equaling a number. So if I were to give you y equal 3, well, here would be the horizontal line that has every y value equaling 3. So example 0, 3, 5, 3, -4, 3. So let's talk about the slopes of these lines. Slope of vertical lines. Well, you know, if you can't remember these, you can always calculate it. But the slope of every vertical line, is undefined. It's also known as infinite slope. If you don't remember that it has no slope, you can actually calculate point 1, point 2, substitute those values into the slope-intercept the slope formula, and what are you going to get? You're going to get a number divided by 0. A number divided by 0 is undefined. Now, what about a horizontal line? Horizontal line has 0 slope. There's a difference. There is a difference between no slope, infinite slope, undefined slope, and 0 slope. Again, you can always pick 2 points on the line, substitute in the x and the y values into the slope formula, and see that you're going to get 0 divided by a number. 0 divided by a number is 0. Now, you should also be familiar with being able to recognize when you have a positive slope, meaning you're rising left to right, and negative slope when you're falling left to right. So positive slope rises left to right, negative slope falls left to right. Now, what if you want to write the slope-intercept form of equation of a line? So here we have slope-intercept form of a line. You need a slope, you need a y-intercept. Well, what if I give you a graph? Can you get that information from the graph? Of course you can, especially if you have the graph passing through the y-axis. If the graph is passing through the y-axis, right there, it's an awfully big point, you have 0, 1. So I can identify the y-intercept. Since the y-intercept is 0, 1, b is 1. Now, can I find the slope? Sure, I can find the slope. How do I find the slope? I rise and run to another point. What point do we want to rise and run to? Well, I can identify that one. So 1, 2, 3. I'm going to rise 3, and then I'm going to run backwards -4. So -3/4 is my slope. So if I wanted to write the equation, y equals the slope times x plus the y value of the y-intercept. What if I give you a table of values? And I say, I'd like to explore this a little bit, and I want to write the equation of the line, and I have just a table of values. Well, what you might want to first do is find the slope. If I find the slope, all I have to do is any 2 points, and I don't care which ones you want to pick. You probably want to avoid decimals, so you're more than likely, if I know y'all, will want to pick those 2 points. That's fine. So I'm going to calculate my change of y over my change of x. Again, it doesn't matter which one you're saying is y1 and which one's y2, but you better figure it out. So change of y, this minus this is 4. Oops. And then whichever one you want to choose. Can you get 3/8 as your slope? Don't care. Have my slope. Now, in this case, I have the slope and I have some points. So I could go back to my table and use my slope and substitute into this formula. So y minus y1, which is 1, so this is my 0.1, equals my slope times x minus the corresponding x1. So I am going to distribute. Simplify. Then I'm going to add 1 to both sides. And I have the equation of the line and slope intercept form. Table, if I go back and look at the table, I could also write the slope intercept form using another method. I could, once I identify, because if I look at the back it up and find my slope intercept form by substituting in the slope and then finding B. How am I going to do that? If I only have this information, I can solve for B. If I automatically find the slope, I can pick any one of those points and substitute back in for my x and my y and solve for my b. And then once I have my b, put it in slope intercept form. So let's talk about parallel and perpendicular lines. Slopes, let's say you have 2 lines, line 1 and line 2. If the slopes of the 2 lines are the same, then we would say that the lines are parallel. They never intersect. So if I ask you to write the equation of a line passing through this point, and it's parallel to the line whose equation has this point, well, the first thing you're going to want to do is identify the slope. So the slope of the original line is 2. So I want the equation of a line that passes through this point and has that slope. I could easily substitute into the point slope formula. I know the point, right? So I'm just substituting in. I know the slope. And I can just simplify. Distribute on the right-hand side. Add 3 to both sides. And I'm going to get y equals 2x minus 1. You could graph it to check, right? 1, 2, 1, 2, 3, up 2, over 1. There it is. Yep, works. What if I want to write the equation of a line passing through this point and parallel to this line? Well, first of all, what type of line is this? Y equals 4. The line y equals 4 is a horizontal line. What do we know about the slope of a horizontal line? The slope is 0. And what do we know about the equation of every horizontal line? It's y equals something. So if I'm trying to pass through this point and I'm a horizontal line, I know the line looks like this. What is the equation? Y equals -3. What if I want to write the equation of the line passing through -2, negative? Let me move this up a little bit. -2, -3. Parallel to this line. Well, what type of line is that? That is a vertical line. So what if I know about, a vertical line, it has no slope. A vertical line that passes through this point looks like this. What do I know about equations of vertical lines? They're always x equaling something. X equals -2. Now, that's for parallel lines. What happens if I have two lines that are perpendicular? Two lines that are perpendicular. Two lines are perpendicular if, how are their slopes related? Do we remember? They are negative reciprocals, or opposite reciprocals. So if one line has an undefined slope, then the other one must be a horizontal line with 0 slope. So let's try a few of those. I want to write the equation of the line passing through this point that is perpendicular to this line. So the slope of this line is 2. So the slope of the line that is perpendicular would be the negative reciprocal. So now I'm looking for point slope formula. I substitute in for the point. I substitute in for this slope. So y minus y value, slope, x minus x value. Then let's distribute. So that's y minus 3 equals -1/2 x plus 1. Then I'm going to add 3 to both sides to isolate the y. And there's the equation. What if I want to write the equation of the line passing through this point perpendicular to this line? This line being what type of line? Horizontal. So a line that is perpendicular would be a vertical line with undefined slope. So if it is a vertical line, it's x equal -2. In the next example, I want to write the equation of a line passing through this point perpendicular to this line. This line is a vertical line. So the perpendicular line would be horizontal, so it would have 0 slope. The equation of every horizontal line is y equaling a number. Y equals -3. And you could always graph these to check them. Now, we talked about the point slope form of a line. We talked about the slope intercept form of a line. There is also what is known as the general form of a line, which is this. Coefficients of x and y and c are real numbers, elements of the reals. You've seen this notation before. And a and b can't both be 0. This is the general form of a linear function, linear equation. So, If I were to give you this equation, you should be able to identify A, B, and C. But this isn't in general form because this one is not in general form because the right-hand side is not equal to 0. So if I wanted to show different ways to rewrite this using A, B, and C instead of numerical values, I could easily solve for Y here. This is just you know, a little bit of practice. Oops. I can't talk and write at the same time. So if I subtract those from both sides, that's going to give me by equals negative ax minus c, and then I'm going to divide by b. I'm just solving for y in the general form. And so I could easily, if I knew this relationship, I could easily identify A, B, and C from this equation and substitute in here and immediately get to this. Simplify. And get it in slope-intercept form. This is just showing you that you can do that. But you could also solve the right equation for y. Now, if I wanted to use intercepts to graph this, I could take this general form, and I can show how to solve. Remember, we set to find the x-intercept y equal to 0 and solve for x. Here I would set x equal to 0 and solve for y. I'll leave that as an exercise. You should be able to get x equals negative c over a and y equals negative c over b. And again, once you identify a, b, and c, you could easily just substitute into this to get the corresponding values. I'll leave that as an exercise for you. So that's just general. Now, there is something known as function notation, and you have got to get in the habit of writing things using function notation. We are going to be working with so many different types of functions that we have to really familiarize ourselves with function notation. Plus, we're going to be doing beautiful things to these functions, taking the inverse of functions, looking at different composition of functions. And then in pre-cal, you're going to look at even more types of functions. And then in calculus, you're going to take derivatives and integrate. I mean, it's just going to be incredible. So if you are not proficient with function notation and can't recognize it and write things in function notation, we're going to have a problem. So let's go ahead and talk about function notation. Function notation is a shorthand, efficient, effective way to represent functions. So instead of writing y equals 3x plus 7, where y, the output y, depends on some rule being performed on x, I can literally rewrite y as being a function of x, f of x. So we replace the y, or the output value, the range value, with f of x. So just replace the y with f of x. We read that symbol as function evaluated at x, or f of x. This is f of x notation, function of x notation. So if I were to ask you to evaluate the function at different values of x. In fact, I say evaluate the function when x is equal to 5. You would write that, what is the function f evaluated at x equal 5? So that just means f of 5, or the function at x equal 5. So you're literally just replacing the x value with 5. That's it. That's not multiplication. This is function notation. So the function evaluated at x equal 5 has an output of 22. So when x equals 5, y is 22. So the function evaluated at 5 is 22. Now, let's rewrite this next linear equation, linear function, using function notation. So I'm going to replace the y with f of x. And then I want to evaluate it when x is equal to negative 2. So I want to evaluate f at negative 2. Well, let me change colors. The function of, and I'm just substituting in, I'm saying the function evaluated at negative 2. So I'm substituting in negative 2 for x. So the function evaluated at negative 2 is going to be negative 10. So the point negative 2, negative 10 is a solution to that equation. So now take this function and evaluate it at each of these input values. I'm going to let you do that. And let's see if we all get the same thing. So go ahead and try to evaluate the function at each of these input values. Pause it, do it. Let's see if we get the same thing. So I'm just substituting in different values for x into the rule. This goes to 0. This goes to, I have to get a common denominator, so that's going to give me 1.5. 1, 5 halves, 3. Function evaluated at 2. Oops, that's supposed to be at 2. 3. So my ordered pairs are 0, 2, negative 1, 1.5, negative 2, 1, 1, 5 halves, 2, 3. I could plot those. And graph it. Now, where it gets even more interesting is if I give you an input, can you find the output? If I give you an output, can you find the input? So the hardest part that people have is trying to figure out what you've been given. Have you been given the input? Have you been given an x value? Or have you been given an output? Well, if I want to solve this equation, for that, what have I given you? Have I given you the input or the output? Well, I've given you the output. I've told you y is 0. That's function notation. So all you're doing is you're coming here, substituting in 0 in for y and solving for x. So when x equals negative 2, y is 0. Okay, again, you've been given an output. Solve for the x for when the output is negative 5. So when x is 5/3, y, and I don't have to write f of x. I can write g of x or h of x or z of x. Here I've been given an output again. Couple different ways I can approach this. I could distribute the negative 2 on the right-hand side, but boy, I could easily just divide both sides by negative 2, make the problem easier. So when x is 4, y is -6. And last but not least, right-hand side is where I'm going to solve for t. Okay, now I need to solve for t. So what am I going to multiply both sides by? 3. And so that gives me -12 equals t. So when my input is -12, my output is -2. Let's just do a quick little review using multiple different representations. Again, if I'm looking at these, hopefully you recognize that I have been giving you outputs. So I'm looking for the x values for each of those outputs. So in the first one, let's go ahead and do the first one here. I'm looking for the output 4. The output is 4 when the input is 2. In the table, the output is 4. Ooh. 2 times. Okay, in this one, the output is 4 when the input is 3. Okay, now let's try the next one. I'm looking for when the output is -1. In the first one, doesn't exist. There does not exist an x value where the output is -1. In the next one, there it is. The output is -1 when the input is 0. What about the next one? There we go. The output is -1 when the input is 7. Anything else? Well, how would we write these in function notation just for kicks? The function evaluated at 2 is 4. The function evaluated at 2 is 4. The function evaluated at 4 is 4. The function evaluated at 0 is -1. The function evaluated at 3 is 4. The function evaluated at 7 is -1. So that's just function notation, because we should be able to go back and forth. Now, how do we graph equations on the calculator? You go to the y= button. You put in the right-hand side of the equation, you hit graph, there you have it. So go ahead and try to graph this equation and see if you get a line. And you should be able to double check to make sure that you have a line that has a negative slope. It falls from left to right, and then it passes through the y-axis at 0, -6. Slope is -3. You may have to adjust your window. You're going to have to get comfortable adjusting your window on your calculator. You could also find the y-intercepts. How do we find the y-intercepts? Algebraically, by substituting x = 0, finding y, substituting y = 0, finding x, but the calculator also allows you to do that, and we can talk about that in class.